To determine if a service is adequately sized, perform a load calculation following the National Electrical Code, or NEC. This calculation will determine the minimum ampacity required for the service. The NEC provides guidelines for calculating demand factors and accounting for continuous and non-continuous loads. Firstly, determine the connected loads. The connected loads consist of all electrical equipment that will be connected to the service. In this case, there are 4 LED lamps, each consuming 100 watts, totaling 400 watts. Additionally, there are 2 receptacles, each rated at 15 amps. Assuming a voltage of 120 volts per receptacle, the total receptacle load is 2 times 15 amps times 120 volts, which equals 3600 volt amps, or 3.6 kilovolt amps. Secondly, apply demand factors. Demand factors are used to reduce the calculated load based on the assumption that not all loads will operate simultaneously at the maximum rating. The NEC specifies demand factors for different types of loads in various tables, such as NEC Table 220.42. For continuous loads, which are loads expected to operate for 3 hours or more, a demand factor of 125% is applied. For non-continuous loads, a demand factor of 100% is applied. Thirdly, calculate the total demand. For the lighting load, which is considered a continuous load, the demand is 400 watts times 1.25, which equals 500 watts. For the receptacle load, which is considered a non-continuous load, the demand is 3.6 kilovolt amps times 1, which equals 3.6 kilovolt amps. Fourthly, convert kilowatts and kilovolt amps to amps. To convert the lighting demand from watts to amps, divide the power in watts by the voltage. Assuming a voltage of 120 volts, the lighting demand in amps is 500 watts divided by 120 volts, which equals 4.17 amps. To convert the receptacle demand from kilovolt amps to amps, divide the power in volt amps by the voltage. Assuming a voltage of 120 volts, the receptacle demand in amps is 3600 volt amps divided by 120 volts, which equals 30 amps. Fifthly, add the demands together. The total demand is the sum of the lighting demand and the receptacle demand. In this case, the total demand is 4.17 amps plus 30 amps, which equals 34.17 amps. Sixthly, determine the service ampacity. The service ampacity must be equal to or greater than the total demand. The NEC specifies standard ampacity ratings for conductors and overcurrent protection devices. Choose the next highest standard ampacity rating that is equal to or greater than the total demand. In this case, the next higher standard ampacity rating is 35 amps. Therefore, the minimum service ampacity required for the building is 35 amps. Diversity factors are related to demand factors, but they are applied to multiple loads of similar types, rather than individual loads. Diversity factors account for the fact that not all similar loads will operate at their maximum rating simultaneously. For example, in an office building with many receptacles, a diversity factor may be applied to the total receptacle load to account for the fact that not all receptacles will be in use at the same time. To apply diversity factors, refer to the appropriate tables in the NEC for the specific types of loads being considered. Multiply the total connected load by the diversity factor to determine the demand load. Use the demand load in the service ampacity calculation. The NEC provides guidelines for calculating service ampacity to ensure that electrical services are adequately sized to meet the demands of the loads they serve. By following these guidelines and considering factors such as continuous and non-continuous loads, demand factors, and diversity factors, electrical engineers and contractors can ensure the safety and reliability of electrical systems. In this specific scenario, with 4 LED lamps and 2 15-amp receptacles, and considering demand factors for continuous and non-continuous loads, the minimum service ampacity required is determined to be 35 amps. This calculation adheres to NEC standards and ensures that the service can handle the anticipated electrical demand of the building. The NEC Article 220 provides comprehensive guidelines for branch circuit, feeder, and service calculations. It outlines the requirements for calculating the minimum size of conductors and overcurrent protection devices based on the connected loads and demand factors. NEC Table 220.42 specifically addresses demand factors for various types of loads, including lighting, receptacles, and appliances. It provides percentages that can be applied to the connected load to determine the demand load, which is the load that the service must be sized to accommodate. When calculating service ampacity, it is essential to consider all connected loads, including lighting, receptacles, HVAC equipment, and any other electrical devices. Each load should be evaluated based on its characteristics, such as whether it is continuous or non-continuous, and the appropriate demand factor should be applied. For continuous loads, which operate for 3 hours or more, a demand factor of 125% is typically applied, as per NEC guidelines. For non-continuous loads, a demand factor of 100% is applied. After applying the demand factors to each load, the individual demands are summed to determine the total demand on the service. This total demand is then used to select the appropriate size of conductors and overcurrent protection devices for the service. It is important to consult the NEC and local electrical codes for specific requirements and guidelines related to service ampacity calculations. These codes provide detailed information on how to properly size electrical services to ensure safety and reliability. In addition to demand factors, diversity factors may also be considered when calculating service ampacity. Diversity factors are applied to multiple loads of similar types to account for the fact that not all loads will operate simultaneously at their maximum rating. For example, in an office building with numerous receptacles, a diversity factor may be applied to the total receptacle load to reflect the fact that not all receptacles will be in use at the same time. The NEC provides tables and guidelines for applying diversity factors to various types of loads. These factors can help to reduce the calculated load and potentially reduce the size of the service conductors and overcurrent protection devices. However, it is important to carefully consider the specific characteristics of the loads and the potential for simultaneous operation before applying diversity factors. By considering all connected loads, demand factors, and diversity factors, electrical engineers and contractors can accurately calculate the service ampacity required for a building or facility. This ensures that the electrical service is adequately sized to meet the demands of the loads it serves, while also minimizing the risk of overloading and potential hazards. The NEC is a comprehensive set of standards and guidelines for electrical installations. It covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It is essential for electrical professionals to be familiar with the NEC and to follow its requirements when designing and installing electrical systems. The NEC is updated every 3 years to reflect changes in technology and industry practices. It is important to use the latest edition of the NEC to ensure compliance with current standards. In addition to the NEC, local electrical codes may also apply. These codes may have additional requirements or modifications to the NEC to address local conditions and concerns. It is important to consult with local authorities to determine the applicable electrical codes for a specific project. Service ampacity calculations are a critical aspect of electrical design and installation. They ensure that electrical services are adequately sized to meet the demands of the loads they serve, while also minimizing the risk of overloading and potential hazards. By following the guidelines in the NEC and considering factors such as connected loads, demand factors, and diversity factors, electrical professionals can ensure the safety and reliability of electrical systems. When performing service ampacity calculations, it is important to document all assumptions and calculations. This documentation can be used to justify the selected service size and to demonstrate compliance with applicable codes and standards. It is also helpful to maintain records of load measurements and operating conditions to verify the accuracy of the calculations and to identify any potential issues. Regular inspections and maintenance of electrical systems are also essential to ensure their continued safety and reliability. These inspections should include a review of the service ampacity calculations and a verification of the actual loads being served. Any discrepancies or potential issues should be addressed promptly to prevent overloading and potential hazards. Service ampacity calculations are an integral part of electrical engineering and should not be overlooked or underestimated. Accurate calculations and proper installation practices are essential to ensure the safety and reliability of electrical systems. In addition to the calculations already discussed, it is important to consider voltage drop when determining service ampacity. Voltage drop is the reduction in voltage that occurs along a conductor due to its impedance and the current flowing through it. Excessive voltage drop can cause equipment to malfunction and can reduce the efficiency of electrical systems. The NEC specifies limits on voltage drop for both branch circuits and feeders. It is important to calculate the voltage drop for each circuit and to ensure that it does not exceed the specified limits. If the voltage drop is excessive, the conductor size must be increased to reduce the impedance and the voltage drop. Voltage drop calculations should be performed under worst-case conditions, such as when all loads are operating at their maximum demand. This will ensure that the voltage drop is within acceptable limits under all operating conditions. In addition to voltage drop, it is also important to consider the ambient temperature when determining service ampacity. The ampacity of a conductor is the maximum current that it can carry without exceeding its temperature rating. The ampacity of a conductor decreases as the ambient temperature increases. The NEC provides tables that list the ampacity of conductors at various ambient temperatures. It is important to select conductors with an ampacity that is appropriate for the ambient temperature in which they will be installed. If the ambient temperature is high, it may be necessary to use larger conductors to maintain the required ampacity. The location of the service equipment should also be considered when determining service ampacity. Service equipment should be located in a readily accessible location that is protected from physical damage and environmental conditions. The service equipment should also be located close to the load center to minimize voltage drop. The service equipment should be sized to accommodate the total calculated load, including any future expansion. It is important to select service equipment that is rated for the available fault current. The fault current is the current that would flow in the event of a short circuit. The service equipment must be able to withstand the fault current without failing. The available fault current can be determined from the utility company or by performing a fault current study. Service ampacity calculations are a complex and critical aspect of electrical design. It is important to consult with a qualified electrical engineer to ensure that the calculations are performed correctly and that the service is adequately sized. A qualified electrical engineer can also help to identify and address any potential issues, such as voltage drop, ambient temperature, and fault current. The NEC provides detailed guidelines for performing service ampacity calculations. It is important to be familiar with the NEC and to follow its requirements when designing and installing electrical services. Service ampacity calculations should be reviewed and updated periodically to ensure that the service is still adequately sized for the current and future loads. Changes in occupancy, equipment, or operating conditions can affect the load on the service. It is important to monitor the load and the service and to make adjustments as necessary. In addition to the NEC, local electrical codes may also apply. These codes may have additional requirements or modifications to the NEC to address local conditions and concerns. It is important to consult with local authorities to determine the applicable electrical codes for a specific project. Service ampacity calculations are an essential part of ensuring the safety and reliability of electrical systems. Accurate calculations and proper installation practices are critical to prevent overloading and potential hazards. By following the guidelines in the NEC and consulting with a qualified electrical engineer, you can ensure that your electrical service is adequately sized and installed. In summary, to accurately determine service ampacity, these are the necessary steps. Firstly, identify all connected loads, including lighting, receptacles, and any other electrical equipment. Secondly, determine whether each load is continuous or non-continuous. Continuous loads are those that operate for 3 hours or more at a time. Thirdly, apply the appropriate demand factors to each load. The NEC provides tables of demand factors for various types of loads. For continuous loads, a demand factor of 125% is typically applied. For non-continuous loads, a demand factor of 100% is applied. Fourthly, calculate the total demand by summing the demands of all the individual loads. Fifthly, convert the total demand from watts or volt amps to amps. Sixthly, select conductors and overcurrent protection devices that are rated for the calculated ampacity. Seventhly, consider voltage drop and ambient temperature when selecting conductors. Eighthly, ensure that the service equipment is rated for the available fault current. Ninthly, consult with a qualified electrical engineer to ensure that the calculations are performed correctly and that the service is adequately sized. Tenthly, review and update the calculations periodically to ensure that the service is still adequately sized for the current and future loads. By following these steps, you can ensure that your electrical service is safe, reliable, and compliant with applicable codes and standards.